So warm welcome to the 37th lecture on the subject of digital signal processing, its applications. We continue in this discussion with the efficient realization of the discrete Fourier transform. Yeah, we had initiated the discussion the last time, but we had come to a point where we divided the problem into two smaller sub-problems, and we saw that when we look at the divided problem and thus conquer the problem, it is computationally more efficient. We have a crude estimate of how much of gain we have in dividing the problem into two parts. But today we need to make a much more detailed structure based on the idea that we evolved in the previous lecture. So, let us then begin by reviewing the idea that we had begun discussing in the previous lecture. We had started talking about the decimation in time approach. And what we said essentially was that we would divide the time domain samples into even and odd samples, right? So we said we would write down the discrete Fourier transform with n samples, n being a power of 2 here. We would divide this n-point discrete Fourier transform given by summation xk is equal to summation n going from 0 to capital N minus 1 xn e raised to the power minus j 2 pi by n nk into two discrete Fourier transforms of size n by 2. So this could be written as summation n going from 0 to n by 2 minus 1 x, or we could write n1 if you like, x2 n1 e raised to the power minus j 2 pi by n by 2 n1 k plus e raised to the power minus j 2 pi by n times k. This is independent of n1. And then we are left with summation n1 going from 0 to n by 2 minus 1 x2 n1 plus 1 e raised to the power minus j 2 pi by n by 2 times n1k. Now this was the additional computation, additional multiplication. And the additional computation involved these additional multiplications and the addition of the individual n by 2 point DFTs. So we saw that essentially this is an n by 2 point DFT here. And so is this. Now what we need to do is to see if we can also reduce the computation involved in this. Though of course we have already got some reduction in the crude estimate, we can probably do better. And all that we need to do is to split these frequency indices k into the first n by 2 and the second n by 2. So we could write k goes from 0 to n minus 1 as k goes from 0 to n by 2 minus 1 and k plus n by 2 goes from, you see, now here we could write another index, so let's write k1 and with k1 equal to 0 to n by 2 minus 1 and k1 plus n by 2 again with k1 going from 0 to n by 2 minus 1. So if we do that, then with these two sets of indices, k1 runs here and then we write k1 plus n by 2. We have covered all the n points here. Okay. So let us write down the expression for e raised to the power minus j 2 pi by n times k1 plus n by 2. Now that becomes e raised to the power minus j 2 pi by n times 2 by n, n by 2 inverse. Sorry, 2 by n inverse, so n by 2 here, times e raised to the power minus j 2 pi by n k1. And as you can see, e raised to the power minus j 2 pi by n by 2 is essentially e raised to the power minus j pi. So this is essentially minus 1. The n cancels. And therefore, you have just e raised to the power minus j 2 pi by n times k or k1 multiplied by minus 1. And therefore, for the first n by 2 samples, you just keep the factor as it is. For the next n by 2 samples, you replace it with a negative sign. And that really means that you have best done this calculation before you add and subtract. So that means what we are saying is, we can generate a k1 and we can generate a k1 plus n by 2. These are frequency points, remember. By taking the output on the lower, we have a set of outputs of the discrete Fourier transform of the odd points. You see, look at it. You have a set of outputs of the discrete Fourier transform of the odd points indexed by k. And what you are doing is to take the first n by 2 points and multiply it by e raised to the power minus j 2 pi by n times k, and the second n by 2 points, and there we have a minus sign here. So what we could do better is to multiply, and of course there are, remember, this is an n by 2 point DFT. So for the first k and for the next, for the first n by 2 and for the next n by 2, you have the same set of points. And an n by 2 point discrete Fourier transform is periodic with period n by 2. So, you see, what we have is a structure like this. We have taken the k1th output of the DFT here, of the odd points here, multiplied it by e raised to the power minus j 2 pi by n times k1. Remember, k1 goes from 0 to n by 2. So we multiplied by e raised to the power minus j 2 pi by n times k1. And of course we take the k1th point of the upper or even point DFT here, and we carry it as it is. We add these points to get the upper set of n by 2 points, and we subtract these to get the lower set of n by 2 points. You see, let's fix our ideas. The first thing is that the discrete Fourier transform is always periodic in the frequency variable with period equal to the number of points. So when you have an n by 2 point DFT, it is periodic with period n by 2, not n. So even though you have an index k on the discrete Fourier transform, and that index k varies from 0 to n minus 1, When you are taking an n by 2 point DFT, the first n by 2 values are exactly equal to the next n by 2 values, point by point. So, when we made a division of the frequency index in this way, 0 to n minus 1, split up into k1 and k1 plus n by 2, k1 going from 0 to n by 2 minus 1, then this covers the first n by 2 points and this covers the next n by 2 points, and these points are equal for each k1. So, k1 equal to 0 is the same value as k1 equal to n by 2, or k1 plus n by 2 equal to, or yeah, so essentially you have, if you take k1 plus n by 2 and put k1 equal to 0. Right? So, what I am saying is, in this expression, in this discrete Fourier transform of n by 2 points as we have here, even though the index k runs from 0 to n minus 1, it is essentially a twice repeated DFT, because for the first n by 2 points and for the next n by 2 points we have really the same outputs. Okay? And therefore, we have partitioned the outputs, the frequency outputs, into the first n by 2 points and the second n by 2 points. And what we are saying here effectively is that the first n by 2 points are generated by adding the k1 at the respective point of the even point n by 2, even n by 2 point DFT, and the odd point from the odd n by 2 point DFT multiplied by e raised to the power minus j2 pi by n times k1. We add these and we get the points for the upper n by 2 set. And for the lower n by 2 set, we subtract this from this. That is what essentially we have said when we note that there is a minus 1. This is, this minus is reflected here. Is that clear to everybody? Yeah, so for the first n by 2 we add, and for the second n by 2 we subtract. And that means that we have brought down the number of additional multiplications to roughly half. Because initially we had thought that we would be doing n multiplications, but now we are not doing n multiplications at all. We are only multiplying the lower points, and that to only n by 2 outputs. So at a crude estimate, we have just n by 2 multipliers here. But we'll, if we are even more careful, we'll notice that for k1 equal to 0, there is no multiplication and so on. But anyway, at least now we are better than n. We are at n by 2. So you see, now whatever structure we have here can be generalized to the next n by 4 points. So the whole process is as follows. We are saying that you have an n point discrete Fourier transform. You split this into two n by 2 point discrete Fourier transforms plus n by 2. Now note, n by 2 multiplies for the lower, you can call them lower or whatever you want to call them, lower DFT, plus n adds. And now the n by 2 DFT can also be similarly split. And this can continue recursively. We go until we reach a 1 point discrete Fourier transform. And a 1 point discrete Fourier transform is an identity operation. It is no operation at all. And therefore, we can now write down a signal flow graph for an n point discrete Fourier transform implemented with the fast Fourier transform algorithm based on decimation in time. And we will illustrate this by writing down the signal flow graph for an 8 point discrete Fourier transform. So 8 point DFT based on decimation in time. So let's get the structure correct. From 8 we will have 4 to 4 point DFT plus additional computation. 4 will take us to 2 and 2 point DFT plus additional computation. And we can of course write 2 to 1 to 1, but we can as well show what a 2 point DFT looks like and terminate the matter right there. So a 2 point DFT would appear like this. A 2 point DFT is essentially xk is summation n going from 0 to 1 xn e raised to the power minus j2 pi by 2 times nk, and of course you can easily see that x of 0 is simply x small x0 plus small x1, and x of 1 is simply small x0 minus small x1, because e raised to the power minus j2 pi by 2 is e raised to the power minus j pi, which is minus 1. And now we can draw the signal flow graph for a decimation in time approach. Let us do that. So of course we have to begin from the left, from the right, sorry, and go towards the left, unlike what we normally do. So we have 4 points here, and 4 points there. And let's get, let's visualize the structure. In fact, if you look at it carefully, what you're doing here is a 2 point DFT of these 2 points. Look back at this expression. x0 plus x1 is capital X0, x0 minus x1 is capital X1. So this sum is the first of the 2 points, and this difference is the second of the 2 points. So essentially this is a 2 point DFT here. And we are going to repeat this structure 4 times in every step. So let's visualize it. So this point and this point are added to produce the upper point and subtracted for the lower. And you can draw the, now this is often called a butterfly because of its appearance. So we have 4 butterflies. This completes the 4 butterflies here. Now here we have multipliers. And in fact, we are drawing an 8 point DFT, so n equal to 8. And therefore here you have e raised to the power, and here you would, in the first step, let's write it down separately. raised to the power, let's do some rough calculation. E raised to the power minus j 2 pi by 8 times k or k1 going from 0 to 3 are essentially 1 e raised to the power minus j 2 pi by 8 e raised to the power minus j 2 pi by 4 and e raised to the power minus j 3 times 2 pi by 8. So we have only 3 multipliers, not 4 actually. One of them is a trivial one. 2 pi by 8 here, e raised to the power minus j 2 pi by 4, 2 times 2 pi by 8 and 3 times 2 pi by 8. These are the multipliers here. And these are transmitted as they are. Now here we would be doing a 4-point discrete Fourier transform. And here also we would be doing a 4-point discrete Fourier transform of the 4 points. Here it would be the 4 even points and here it would be the 4 odd points. But we can do the same decomposition for the 4-point discrete Fourier transform. So we bring these butterflies here again. Now instead of 4 and 4, you have 2 and 2. These are the butterflies now. And now we need multipliers here and here. And for these multipliers, we need to figure out what the multipliers are. Now remember, we are doing a 4-point discrete Fourier transform here. So the multipliers would be of the form e raised to the power minus j 2 pi by 4 times k. And you would have 4 by 2, that is 2 of such multipliers. And therefore we do that rough work again. E raised to the power minus j 2 pi by 4 times k1. k1 goes from 0 to 2. That is essentially 1 and e raised to the power minus j 2 pi by 4. That's e raised to the power minus j pi by 2. Actually, e raised to the power minus j pi by 2 can as well be written as minus j. So here we are. We have a trivial multiplier here and minus j there. And the upper points get transmitted as they are. So we have completed the second step. Now we are left with 2-point discrete Fourier transforms. And 2-point discrete Fourier transforms, we know how they look. Those are very simple. The 2-point discrete Fourier transforms simply look like this. They are just butterflies. Now what we have here is x of k, capital X of k equal to 0, 1, 2, 3, 4, 5, 6, 7.
Sir?
Yes, there's a question.
Why didn't we multiply with minus j in the other two DFTs?
So the question is, why don't we multiply by minus j? No, we do. I didn't, oh, I'm sorry. So you see here, no. See, please remember that when you're doing the 4 point, the question is, why don't we put minus j's here? Is that the question?
The lower one. Then.
Here, this one? Here? Oh, because you see, this is, the question is, why don't we put a minus j here? Well, what you're doing is to put multipliers. Now look at, go back to the original drawing here. You see, when you have an 8-point DFT, you're pairing 1 point from the upper and 1 point from the lower group. And in the lower group, you're multiplying by e raised to the power minus j 2 pi by n times k1. And this runs over half the points. Now, so now let's look at what we are doing here. The 4-point discrete Fourier transform. You see, here we're trying, now up to here, we have reached a point where we need to calculate a 4-point DFT here. So in a 4-point DFT would have butterflies like this for the upper group of 2 and lower group of 2. Again, upper group of 2 and lower group of 2. And only in the lower group of 2 do we have multipliers. And even among those multipliers, the first one, as you see here, is for k1 equal to 0, that's 1. And the second one is for k1 equal to 1, which is minus j. And therefore, actually, you have only one multiplier. Is that clear? So is that clear how we've arrived at this structure? Any doubts on this structure? Now there's one important point which we haven't quite mentioned explicitly, namely, how are you going to arrange the points here? Now, when we came up to here, we have put the even points on the top, even points of the input on the top and the odd points beneath. When we came here, we took the even out of these and put them on the top, and the odd out of these and put them on the top, put them beneath. And the same is true of this group of 4. And then of course we computed the 2-point DFT. So let's see what we actually did. What we actually did was to begin with 0, 1, n. 0, 1, 2, 3, 4, 5, 6, 7. And we took the even points and put them here. So 0, 2, 4, 6, 1, 3, 5, 7. In the second step, we took the even among these, that is 0, 4 and put them on top, and 2, 6 and put them beneath. And then we took the even out of these and put them on top and the odd beneath. Now let us write down both these sequences in binary. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. 1, 0, 0, 1, 0, 1 and so on. And let's write down this in binary as well. So we have it is very interesting. What we have done is to reverse, take each pair in turn. What we have done is to reverse the order of the bits. in each of them. And this is not surprising. You see, when you separate or partition the even points on the top and the odd points beneath, you are giving the greatest importance to the least significant bit. The least significant bit is either 0 or 1 depending on whether the number is even or odd. If the number is even, it is 0. If the number is 1, it is odd. And therefore, in partitioning with the even on top and the odd beneath, you have given the greatest importance to the least significant bit. So, you have made the least significant bit the greatest. And you are doing this every time. And of course, when n equal to 8, you will have 3 bits in your representation of the numbers. And therefore, each time you are taking the least significant bit and putting it into the greatest significant position. And therefore, you have a bit reversal taking place. So that's, see, this bit reversed ordering of the input is required to get in order or in place calculation of the output. Of course, you can always redraw the signal flow graph. You have 8 inputs in the signal flow graph and 8 outputs in the signal flow graph. And of course, you have interconnections. So, it is perfectly possible to redraw the signal flow graph so that you have the inputs also in order and the outputs also in order. You just need to rearrange the edges. And in fact, I leave that to you as an exercise. Redraw the signal flow graph so that both n and k are in place. That means n is not in bit reversed order. That really means you have to rearrange and replace the edges. If you like, you can think of these edges as threads connecting a number of pins. And all that you are doing is, you see, you have several pins already connected by threads. All that you are doing is you are rearranging the pins on the board. The threads are carried with them. To think of it like that. So, it is perfectly possible to redraw the signal flow graph so that you have both n and k in place, right, if you really want to do that. Now, you see, what we have done here is to decimate in time and to partition in frequency. Naturally, the principle of duality tells us that there could be exactly a dual approach to this. We could partition in time and decimate in frequency. So, let us indeed do that now. But before we do that, let us get a precise estimate of how much we have gained in going from the direct 8-point discrete Fourier transform to this decimation in time fast Fourier transform. So, how many multipliers do we have here really? I am not counting -1 as a multiplier, because in most hardware realizations, multiplication by -1 can be done by what is called 2's complementation. And 2's complementation really involves just reversal of bits and an addition of a 1 in the end. So, there is not much of multiplication involved in multiplication by -1. And therefore, multiplication by -1 is essentially just a little bit of operation on the bits. There is no real multiplication. Some people also like not to regard multiplication by j as a multiplication, because they feel that you can think of multiplication by j or -j essentially as movement from real to imaginary or imaginary to real. So, when you are writing down, of course, here you must realize that even if the input sequence is real, the output is complex, and therefore you must think of the input and the output as complex here. All the computation is complex. And anyway, that's a good idea, because the inverse 8-point discrete Fourier transform can be implemented by almost a similar structure, except that you need to replace m by minus n or k by minus k. You can think of it either way. And that means the same structure essentially can be modified with a little bit of tweaking of the signs to get an inverse 8-point discrete Fourier transform. And in fact, I leave that to you as an exercise as well. Exercise: redraw the same signal flow graph that is the decimation in time to represent an 8-point inverse DFT. Now let's get a precise idea of the multiplications and additions. You see, we have clearly 8 additions here, and so also here, and so also here. So we have 8 3s are 24 adds. There are no other adds, if you can see. And how many multiplies do we have really? We have only 1, 2, 3, 4, in fact this one and this one. 1, 2, 3, 4 and 5, that's all. Only 5 multiplies. This signal flow graph has only 8 3s are 24 multiplies, and adds, and 5 multiplies, non-trivial multiplies. Now let's also get a clear estimate of how many multiplies and adds we have in the original 8-point discrete Fourier transform. You see, for that we need to construct a table. Adds is easy. If we calculate the 8-point DFT directly, we have 8 times 7, which is 56 adds. That we cannot do much about. I mean, you see, here we are talking about 2 input additions, of course. We want a uniform architecture, so we are talking about 2 input additions. You would have 8 into 7, 56 2 input adds. And let's see how many multiplies. For the multiplies, we need to construct a table. We need to write a table of n's and k's. The n on this and k here. N can take the value 0, 1, 2, 3, 4, 5, 6, 7, so can k. And therefore essentially you have e raised to the power minus j 2 pi by 8 times mk. This is the factor which we have to see, where there is a non-trivial factor and where is a trivial factor. Now you see, when either n or k is 0, there is no multiplication at all. So we can cut off this entire row and column. That's just a multiplication by 1. Similarly, when n is equal to 4 or k is equal to 4, you get e raised to the power minus j 2 pi by 8 into 4, which is e raised to the power minus j pi, which is minus 1. So essentially you have minus 1 to the power of nk. That is either minus 1 or plus 1. That's not a multiplication at all. So we can drop off the entire column with 4 and the entire row with 4. And we shall of course continue to consider multiplication by j and minus j as multiplies. We will consider them as multiplies. So now we are left with 1, 2, 3 here, 9 of them, and we have 9 times 4. That's 36 multiplies. So we have 36 non-trivial multiplies in the direct implementation and only 5 of them in the fast Fourier transform. So of course now we see the advantage very clearly. Last time we did a crude estimate, but now we have done an accurate estimate of exactly how many multiplies and adds we have in the original direct implementation and in the fast Fourier transform implementation. Now, as I said, we can invoke the principle of duality, and we could do what we did in time on the frequency index. So let's do that. Decimation in frequency. The idea is very simple. We write down the same discrete Fourier transform. But now we separate k into 2k and 2 or 2k1 and 2k1 plus 1. k1 going from 0 to n by 2 minus 1. And taking experience from what we had in the decimation in time, we partition the time index into the upper and the lower n by 2. You see, when we did decimation in time, we had to partition the frequency axis into the upper n by 2 and the lower n by 2. So here we partition time into the upper n by 2 and lower n by 2. So we partition n into n1 going from 0 to n by 2 minus 1 and n1 plus n by 2. Of course, n1 again going from 0 to n by 2 minus 1. And therefore, we now have a simple expression for the discrete Fourier transform. X of 2k1 is summation n1 going from 0 to n by 2 minus 1 x n1 e raised to the power minus j 2 pi by n times n1 into 2k1 plus summation n1 going from 0 to n by 2 minus 1 x n1 plus n by 2 e raised to the power minus j 2 pi by n n1 plus n by 2 into 2k1. Remember, 2k1. This is one part of the expression. This is for the even points of the frequency index. And now we write down the expression for the odd points. The odd points are x 2k1 plus 1. And they go as, so again summation n1 going from 0 to n by 2 minus 1, x n1 e raised to the power minus j 2 pi by n, of course n1, but 2k1 plus 1. And summation n1 going from 0 to n by 2 minus 1, x n1 plus n by 2, e raised to the power minus j 2 pi by n, n1, not n1, but n1 plus n by 2 times 2k1 plus 1. Now we need to make a few simplifications here. The first simplification that we need to make is on the term e raised to the power minus j 2 pi by n times n1 plus n by 2. So let's make that simplification. E raised to the power minus j 2 pi by n into n1 plus n by 2 is essentially e raised to the power minus j 2 pi by n into n1 times e raised to the power minus j 2 pi by n into n by 2. But this is minus 1, so that's minus e raised to the power minus j 2 pi by n times n1. So essentially what we have here is that this is the negative of this. You see, so now we can make matters easier. We could rewrite with this change, we could rewrite the two expressions for x2k1 and x2k1 plus 1. We could rewrite x2k1, look back at the expression here, we could rewrite it, keep this, now here again we can take the 2 in the denominator, so n by 2, we want to get an n by 2 point DFT. Here also we can do it by taking 2 here, and we can keep this as minus 1. So but please remember, we should write minus e raised to the power minus j 2 pi by n times n1 to the power 2k1. So that gives you a minus 1 raised to the power 2k1 into this raised to the power 2k1. And so actually the minus 1 goes away here. So this is equal to summation n1 going from 0 to n by 2 minus 1 x n1 e raised to the power minus j 2 pi by n by 2 times n1k plus summation n1 going from 0 to n by 2 minus 1 x n1 plus n by 2. Now again, you have a minus 1 raised to the power 2k1 times this raised to the power 2k1. And this raised to the power 2k1 can be simplified by bringing the 2 into the denominator. So minus 1 raised to the power 2k1 is 1, and therefore you have e raised to the power minus j 2 pi by n by 2 times n1 k1. On the other hand, for 2k1 plus 1, what we need to do is as follows. Of course, this part, if you look at it, here you would not be so lucky, because here this is minus e raised to the power minus j 2 pi by n1, and this is raised to the power 2k plus 1. So let me identify that part of the expression. x2k plus 1, k1 plus 1 is summation n1 going from 0 to n by 2 minus 1, x n1. Now here what I am going to do is to split this into two terms, one involving 2k1 and the other involving just 1. So e raised to the power minus j 2 pi by n times n1 into e raised to the power minus j 2 pi by n times, rather n by 2 times n1 k1. Plus summation n1 going from 0 to n by 2 minus 1, the same thing holds, except that now we need to write x n1 plus n by 2 e raised to the power, now e raised to the power minus j 2 pi by n, n1 plus n2 is essentially minus e raised to the power minus j 2 pi by n times n1. And this is now raised to the power 2k plus 1. So the minus 1 sign remains. Times minus 1. The minus 1 sign persists. Now I am going to leave the rest of it for you to complete. And let me give you the idea and then you can complete the remaining signal flow graph. What you need to do is to look at these two expressions carefully. Now, as we did for the decimation in time approach. Essentially, you notice that these are two n by 2 point DFTs here. And these are also two n by 2 point DFTs, except that, you're going to get e raised to the power minus j 2 pi by n by 2, and you're also going to get another e raised to the power minus j 2 pi by n by 2 times n1 k1 coming from this term here. But you have some additional multiplications, and for the even points you have a sum, and for the odd points you have a difference. Now, exactly like you did for the decimation in time approach, in this decimation in frequency approach, you would also have to do a rearrangement of the order of multiplication and the butterfly. So, in fact, I put the result before you, but leave it to you to verify as an exercise. The result exercise, verify that this leads to a signal flow graph which is the transpose of the earlier one, of the decimation in time. By a transpose, we mean a signal flow graph where all the edges are reversed in direction, but they carry the same multiplies, and wherever there was a branching it becomes an addition, and wherever there was an addition it becomes a branching as a consequence of the reversal. So, a transpose means reverse the direction of all edges of the signal flow graph. Now, of course, here, because the number of inputs and the number of outputs is the same, transposition is going to result in the same structures, or in a similar structure, if not the same. If you had a different number of inputs and outputs, of course, that would be reflected when you transpose. Of course, if you have only one input and one output, It is a celebrated theorem in signal flow graphs that when you transpose a linear signal flow graph with one input and one output, the input-output relationship remains unchanged. Now what we have illustrated is a special case of this celebrated theorem in the context where you have the same number of inputs and outputs. So I leave it to you as an exercise to verify that the equations that we wrote down actually result in a signal flow graph which is the transpose of the decimation in time signal flow graph. And I also leave it to you as an exercise to calculate how many multiplies and adds you would require for the decimation in frequency. In fact, it would turn out that the number is exactly the same. 5 multiplies and 24 adds. So there is no difference in computational requirement between decimation in time and decimation in frequency. But of course, there could be other differences, and that is a matter of deeper reflection. What other differences are there between decimation in time, and would you in some circumstances prefer one over the other when you are considering, of course, if you had infinite precision there was no issue, but when you have finite precision, is there any other issue to be considered when you choose between decimation in time and decimation in frequency? So with that then, we end the lecture today and we proceed in the next lecture to look at further extensions of the fast Fourier transform. Thank you.